Thanks to all the organizers for this opportunity. So I am hoping, for those of you who are not familiar with reionization and dwarf galaxies, that I'll convince you that it's very important to understand reionization and how it impacts dwarf galaxies when you make your dark matter constraints with them. For those of you, I'm looking at the astrophysicists in the room who are well aware of what reionization does. I hope you'll find this a nice refresher and also find some interesting food for thought. Okay, so yesterday we heard from a lot of model builders and saw many beautiful power spectra, very diverse. In order to test them, we need to translate them, as we discussed during Francis Yan's discussion, into halo mass functions. We can also not see halos, though, so we need another step to turn halos into observables, which are galaxies. So in order to do this last step, we use often what's called a stellar mass-halo mass relation. Some of you may have heard of this being described as the galaxy-halo connection. This is the same thing. And this is what it looks like at dwarf scales. So what you're seeing here is the stellar mass of these halos plotted with the halo masses in the M200 definition. And you can see that at the high mass end, that these two quantities correlate very strongly with each other. But as you get to lower and lower halo masses, these start to diverge a lot. So what you're looking at here in the different points, the ones with the error bars are the ones from observations. The ones without the error bars are ones from simulations. And then these bands up at the top represent abundance matching relations, which sort of combine the two. So this is a bit concerning. There's about 2 orders of magnitude, if not more, difference between these different studies. And I think as astrophysicists in the room know full well how important this is for most studies that touch dwarf galaxies. It impacts our forecasts for what we're going to see in future surveys. It impacts how much of a role we think dwarf galaxies play in reionizing the universe. It impacts, too, our guess as to what the lowest mass halo with the galaxy is. But for the particle physicists in the room, too, I think you should be worried because this impacts our dark matter constraints based on dwarf galaxies. Some work that I've done along with Annika Peter in the past few years showed that basically, depending on what you assume for the stellar mass-halo mass relation, you can be in a missing satellites problem. You could have no missing satellites problem. You could be in a too many satellites problem. It also impacts whether or not a too big to fail problem exists. Shea, Garrison, Kimmel wrote a nice paper on this. That depends on not just where you think the stellar mass-halo mass relation lies, but also the scatter that you assume for it. And you can see all these different simulation studies, the observations, predict that the relation lies in very different places. They also don't agree on how much scatter exists and what slope it should have. So it'll impact all these small-scale problems that we know and love. And so this is also something that goes into all of these small-scale constraints based on Milky Way dwarf galaxies. A lot of the work that Ethan Nadler, for instance, and company have done, the work that I have done, makes some assumption about what the stellar mass-halo mass relation looks like. So it's really important to understand what this looks like and why it looks the way it does. So it turns out we have a wonderful data set to study this in detail, and that is the EDGE simulations. So the EDGE simulations are a very, very high resolution suite of dwarf galaxies. You can see this is the apparent void volume from which we drew our dwarf galaxies. And then around it are these mugshots of these 10 to the 9 solar mass halos that we zoomed into and modeled with very, very high resolution. We're talking about 3 parsecs in spatial resolution. So we're resolving each individual supernova that go off in our simulations. So we're a little less prone to subgrid physics than some lower resolution simulations are, but not fully immune. So what makes EDGE so great, and another really cool aspect about EDGE is that it has what we call genetically modified halos. So what we're looking at now is this halo in particular, halo 1459. That is in this dark purple line here. And what I'm showing is its halo mass over time, or redshift. What this genetic modification does is we change the accretion history so that it evolves more slowly, like you see in these 2 realizations in blue and green. We can also modify it so that it grows more quickly. So that's what you see in this purple line here. The thing that we found when we did these experiments is that that really changes the dwarf galaxy that forms inside it in many, many ways. And the one way I'll focus on here is how it changes its stellar mass. So you can see for all these different realizations, basically the earlier forming the galaxy or the halo is, the more stars it forms. And the sort of differences in accretion histories that we sampled here resulted in 1 order of magnitude difference in the stellar mass that they formed. This is huge. And this could explain, this would be a really, really important part of why the stellar mass-halo mass relation looks the way it does. Okay, but this is one galaxy that we did an experiment on. In order to really constrain the stellar mass-halo mass relation, we need data from thousands, if not tens of thousands of galaxies. That's impossible to do with full hydrodynamic simulations like EDGE. And so I created a new tool called DarkLight to bridge this gap and generate, based on what we've learned from EDGE, populations of dwarf galaxies where we can do more statistical studies like the stellar mass-halo mass relation. I won't go into the details of how DarkLight is built, but this is what's at the heart of DarkLight. So what we noticed was in EDGE was that the star formation rates correlate very strongly with some measure of the halo properties. In our study, we found that it particularly strongly correlates with the maximum of the rotation curve of the halos, just because that probes the halo properties at closer to the center of the halo where all this star formation is occurring. One thing that we have in our models that isn't necessary in a lot of other galaxy halo models is that we adopt 2 star formation Vmax relations, one before reionization, which I show in the black here, and then a different one where the star formation rates are suppressed for the low mass halos after reionization, which is shown in the blue. So we ran this on some of our EDGE halos that have the full hydrodynamic simulations, the ones that take months to run. The results from those in terms of stellar mass over time is shown in the black here. And then I ran DarkLight, which you can generate hundreds of realizations of a galaxy for a single halo in a matter of seconds. And we found that not only is it fast, it's accurate. So you can see in blue here are the predictions from DarkLight, and they match really well with the HydroSims. So great. We have a great tool. So now we went ahead and ran this on a very, very large cosmological volume to try and get a statistical sample of dwarf galaxies. So here, again, is our stellar mass-halo mass relation. Now, in gray are all the predictions by DarkLight. And you can see already there are some really interesting features here. I'll highlight a couple of these. It looks like as we get to smaller and smaller mass scales, the scatter in the stellar mass-halo mass relation predicted by DarkLight is increasing. This is not surprising. This has been found in many, many simulation studies, semi-empirical, semi-analytic. It's been explored in observational work. So this is not surprising. To give a bit more of a number to this, at 10 to the 9 in halo mass, we find a scatter of about half a deck. This is basically spot on with what Ethan Nadler predicted from the Milky Way dwarf galaxies. Okay, but heading towards dark matter constraints, it's really good to understand why it has this increasing scatter. So let's dig into that a little bit more. I mentioned earlier that the edge simulations are great because we have these genetically modified halos, or we saw that if you formed earlier, you have more stars and vice versa. And now we have a full statistical sample where we can actually probe this in detail, and we find that that really does hold up. So what I've done now is basically take the galaxies from DarkLight and bin them in terms of their formation times. So what I've defined that to be here is the time it took each halo to reach 50% of its final mass. And you can see that the early formers, which are in blue, all sit at the very top end of the stellar mass-halo mass relation, whereas all the later formers, which are in the red, form systematically towards the end, the bottom envelope of the relation. So there's this interesting systematic trend. Keep in mind, though, that basically all of the halos that live in this bottom left corner are all quenched by reionization forever, basically. They haven't formed stars since reionization. And so basically, the amount of stars that these were able to form were all formed before then, and so were determined by how much mass these halos were able to achieve before reionization. And so the picture you should be seeing here is that there's this interplay between accretion histories and reionization that really sets the stellar mass-halo mass relation at this very low mass end. Another really interesting thing we can do with DarkLight is basically rewind this stellar mass-halo mass relation backwards in time. And so we did that. I basically rewound this to the point where dwarf galaxies began to get quenched, which happens fairly late in our simulations at about a redshift of 4. And you can see that instead of having this increasing scatter that we see at z equals 0, it had a constant scatter of about 0.2 dex. Now, those of you who are familiar with stellar mass-halo mass relations might find this number surprising, because this is the sort of scatter we see at the high mass end today. And it's only because of reionization and the subsequent growth of these halos since then that causes this increasing scatter to appear. There's two parts to this. One is that I talked about how accretion histories are so important. Each of these halos have a large range of accretion histories, and so you'll see them drift over to the right, which is more halo mass, to differing degrees, so the scatter broadens. But this doesn't explain why it increases, the broadening increases that towards the lower mass end. Why doesn't it just uniformly increase? And that's because of the amount of stars that these galaxies are accreting. So the high mass halos sitting up at the top here tend to accrete halos that do have stars in them. And so what happens is that as they accrete mass, they accrete up along this track and stay roughly in that track. Whereas all the halos down here, these halos tend to be dark and not have any stars in them. And so what happens is that because they are, like we were talking about, accreting different amounts of dark matter, some of them will be accreting more and less, and so you'll have much more of a broadening at the low mass end. So this is why we're getting this increasing scatter at the low mass end. This is interesting, and it'll be impacted by a lot of uncertainties that we have on reionization quenching. So I'm going to show this by simplifying the stellar mass-halo mass relation predicted by DarkLight into this, where I showed just the median relation and just the 1 sigma bands. This biducial relation that I ran had, as I said, a quenching time of z equals 4. You can see it has maybe a slight decrease in the slope at the low mass end, and of course has that half-deck scatter at 10 to the 9 halo mass. If I set reionization to occur later, you can find that the relation becomes basically a single power law. It has no knee. The stellar masses are boosted up because things have had more time to form stars. As you might imagine, there's less time for things to accrete dark halos, and so the scatter in the low mass end decreases by 10% or so. Same thing if you go to earlier reionization quenching. There's a stronger knee, the slope decreases, and there's another 10% increase to your scatter. And in fact, this allows us to reproduce later or earlier quenching allows us to reproduce results from things like the marvelous Dwarf and DC Justice League simulations, like Faram talked about or published on a few years back. They found a very strong knee in their simulations, and they have earlier reionization than we do, so that was reassuring to see. The other thing I mentioned is that it really depends, the amount of scatter you have really depends on accreting dark subhalos. So it turns out if you change the number, the fraction of halos that are dark, so what I've done here is say only halos that have 10 to the 8 solar masses or more have stars in them, then you get this stellar mass-halo mass relation shown in the black. If you say lower mass halos all the way down to 10 to the 7.5 can contain galaxies, then you find that, as you might expect, the stellar mass-halo mass relation shifts up, and the scatter decreases by quite a lot, about 0.07 dex. So occupation fraction is also very important to understand. Okay, so we're interested in dark matter constraints, and this is something I promised you could constrain potentially by understanding reionization and the stellar mass-halo mass relation better. So let's take a look at that. Different accretion histories, dark matter models with different accretion histories are going to predict different stellar mass-halo mass relations because of these effects that I mentioned. So as a poster child, I'll talk about one warm dark matter-like model. So we're running in our next generation edge simulations a bunch of warm dark matter halos, ranging from 3 to 6 keV. And you can see already the classical picture of there's much less substructure in these warm dark matter simulations, including even at 6 keV. So these are all very preliminary, but I ran warm dark matter on the dark matter only versions of these simulations. So this is preliminary because DarkLight needs to be calibrated on the full hydro simulations that we're running now. But from taking a peek at the full hydro simulations, the general picture here holds, even if the exact numbers are different. So what I'm showing here now is for this halo run in CDM, and the star formation histories are shown by the histogram here over time. And you can see, if I flip to what I predict for warm dark matter with DarkLight in the 3 keV thermal relic model, that there are some interesting differences that show up. So I'll flip back and forth between here, and hopefully you'll notice that because halos are forming later in warm dark matter, star formation starts later. But not only that, the warm dark matter halos have lower concentrations, and so they'll have lower Vmaxes, which means that, as I mentioned, my star formation rates are all dependent on Vmaxes, so they will be lower in warm dark matter models. And so what this means is that not only will there be fewer warm dark matter halos, they'll also be fainter. So this may change systematically the stellar mass-halo mass relation. And if you start thinking about what this means for satellite constraints, it could provide even tighter constraints on warm dark matter. Okay, so I am very privileged to be working with a large number of brilliant folks to make DarkLight bigger and better. This is, in particular, an extension I'm showing here to include sizes, how dwarf galaxy sizes change. This is led by my student Sushanta Nigudkar. He just finished his MSc, his master's at UCL this past year, and is now interested in applying to PhD programs. So if you're interested in having a student who's incredibly brilliant, creative, and loves machine learning, I might have someone for you. But he's been looking at how reionization impacts the sizes of dwarf galaxies. They're also truncated in very correlated ways to their accretion histories. And he developed this really cool new particle tagging method that's based on angular momentum rather than the traditional binding energy approach to predict the sizes of dwarf galaxies in dark matter-only simulations. So you can see that the results from the simulations are in the black, and the results from his angular momentum tagging tool is in red, and they agree very, very well in predicting the half-light radii of these galaxies. And they also do really well in predicting the 2D spatial distribution of the stars. So if you want to look at stellar halos, this is a great tool to do that with. Reionization also has these interesting effects, like being able to produce split population dwarf galaxies. Basically, when you throw two quenched dwarf galaxies at each other, they can incite a giant starburst that forms a second population of stars, and then they have these, astronomers will know, these split CMDs, which that, for some people, will immediately spring a light bulb in your mind. Some globular clusters have been seen to have this, so this raises the question, could globular clusters be really tightly stripped dwarf galaxies? And if that's the case, that would really have a lot of implications for dark matter. So the student who's leading this work, Izzy Gray, who's a PhD student at Surrey, is working with me to build this into DarkLight as well. So one last thing I'll end on. DarkLight is just one of many galaxy formation models out there. And there are a couple very popular tools out there that actually do not include any of these effects that I mentioned that are imprinted by reionization. In particular, StatGen doesn't have reionization included in it. Universe Machine, which a lot of the Milky Way dwarf galaxy constraints are based on, also doesn't have reionization. So if you're trying to constrain, especially the ultra-faint, really low-mass dwarf galaxies with any of these tools, keep this in mind. Okay, so I'll end there. DarkLight is open source. If you want to use it, feel free to contact me. And yeah, I hope I've convinced you that reionization and the stellar mass-halo mass relation are really important to understand in dark matter constraints.